Welcome back to our little corner on the web, where we hope to inspire and nurture interest in math. Today, we'll go through question 11 in part 1 of the 26 PMO area stage. Question 11 says, for positive integers p, a, b, and q, let open bracket p, a, b, q, close bracket, be the sum of the first and last digits of p to the power of a plus b to the power of q. For example, open bracket 2, 10, 10, 3, close bracket, is equal to 2 plus 4 equals 6. Since 2 to the 10 plus 10 cubed is equal to 1024 plus 1000, which is 2024. Consider the values of P, A, 10, Q for all PAQ such that P is less than or equal to 10, A is less than or equal to 10, and Q is greater than or equal to 10, but less than or equal to 20. And the integers P and Q are prime numbers. Give the first 3 digits of the sum of all these values. Note that if a value of PA10Q appears more than once, then it should be considered in the sum as many times as it appears. There seems to be a lot going on in this problem, so we'll try to unpack it one at a time. Okay. So B here is fixed at 10, so we don't really have to worry about that. So P is given to be less than or equal to 10, but also a prime number. Likewise, Q is between 10 and 20, but also a prime number. So that actually is a very short list. P can only be 2, 3, 5, and 7. And Q can only be 11, 13, 17, and 19. So one such quadruple might be 2, 8, 10, 11. And we play around with this, you'll notice that 2 to the 8 is actually very small relative to 10 to the 11, meaning one hunch might be P to the A is very small compared to B to the Q. Okay, so here that happens. We have 256 plus, 10 to 11, meaning 1 and 11 zeros after. So the leading number will always be 1. So let's try to see if that's always true. Okay. So we know that 10 to the Q is 10 plus 10 and followed by Q zeros. So the minimum value for the set that we have here is 10 to the 11. So the minimum of B to the Q is 10 to the 11, and the maximum of P to the A is 7 to the 10. So if we write that out, we know for a fact that the upper bound of P to the A is 7 to the 10, which should be strictly less than 10 to the 11. And that is the minimum value of 10 to the Q. This implies that the leftmost digit of the sum of P to the A plus B to the Q, given the constraints we have, should always have a leading number that's 1. Okay? It doesn't matter what Q we choose. It doesn't matter what P or A we choose. Okay? So our job then becomes a little bit simpler, and it's a question of finding the units digit of P to the A. Okay, because we basically find the units digit of P to the A, add 1, and that's 1 value. And we just need to be able to cycle through with the different values of Q. So we know that the units digit of a product of 2 numbers, meaning when we try raising 2 to a certain power, 3 to a certain power, the product of the units digit, right? The product of 2 numbers, right, with the same unit, with some units digit, is basically the product of their units digit if we were only worried about finding the units digit. So we can start raising 2 to some power and 3 to some power and 1 at a time and find P to the A. So 2 to the 1 we know is 2. 2 squared is 4. 2 cubed is 8. And as we multiply it, we just really need 8 times 2 in the units digit, 6. And then here we can throw away the 10 for the 6, 16. And then 6 times 2, and so on and so forth. And we'll find a pretty neat pattern. I mean, it repeats every cycle of 4, which is 2, 4, 8, 6, 2, 4, 8, 6, 2, 4. We just actually needed this pattern, and some of you might have just jumped directly to it. Hence, PABQ is no more than those numbers plus 1. Okay, for this set. So that means that for example, for Q equals 11, we have 3597, 3597. So for Q equals 11, we can just find the sum of these and then multiply it by 4 to have Q equals 11, 13, 17, 19. Okay, so for all values of 2, comma A, comma 10, comma Q, okay, we have the sum being 224. Okay, so now we just have to cycle through P, okay, which is this we're currently 2, and find the other values, okay, the other sums. So for 3, we can go through the same exercise, or some of you might just say, oh, I also know that the pattern repeats every 4, so 3971, 3971. We just need to add 1 to it. So we end up with 41082, 41082, 410. Once we sum it, we have 62 for all values of 3A10Q for a given Q, and we need 4 of those. We know that there's 4 of those Qs. So now for this, for P equals 3, that satisfies the constraint, the sum is 248. For P equals 5, this is a little easier. The units digit doesn't really change for P to the A. So we know that the values can only be 6s. So there's 10 of them, 6 times 10. And there's 4 values of Q, 240. And lastly, we just go through it for 7 to the A. Okay, and 7 to the A follows another pattern that repeats every 4. So it's 7931. Adding 1 to it, we end up with 81042, 81042. Summing it up, multiplying by 4 again, we get 264. So the only thing remaining is to add 224, 248, 240, 264. Okay. So the final answer for this one is 976. Okay. We hope you found this video useful and educational. If you did, hit the like button and subscribe. Thank you for watching.